Thank you. Thank you very much. So, greetings for the day, everyone. A warm welcome to you all to this free webinar on the well-test interpretation using MS Excel. We are thrilled to have you join us today. It's my privilege to introduce our esteemed mentor for this session, Mr. Vinod Kumar. Mr. Vinod Kumar is a seasoned professional in reservoir engineering with an extensive expertise in the well-test interpretation and data analysis. His deep knowledge of using tools like MS Excel for analyzing well test data and identifying the key reservoir characteristics has made him a respected figure in the oil and gas industry. Today, Mr. Kumar will guide us through the essential concepts of well test data interpretation using MS Excel. He will teach you today to analyze the well data efficiently, identify critical reservoir properties, including permeability, skin factor, and well bore damage. This session promises to be highly practical and insightful, equipping you with the skills you can directly apply in the real-world scenarios. Without further delay, I now invite Mr. Vinod Kumar to take over and begin the exciting session. Thank you, and over to you, Mr. Kumar.
Thank you, team.
Vinod,
Thanks for the
yes, yes.
uh, brief introduction about the session and myself. I'm privileged to be here with all this participants and the team. So let me share my screen.
You can share your screen. You are the host now.
So can someone confirm, is my screen visible to everyone who are in the call?
Yes, yes, it is visible.
Okay.
Yes,
Okay.
it is.
Okay. So let me start the discussion for today. Well test interpretation using MS Excel. So did anyone use MS Excel before for well test interpretation? Maybe geologists or reservoir engineers or production engineers, anyone in the call? So the first thing is MS Excel is a very powerful tool for, of course, any interpretation. The basis for interpretation is brought to every industry, every domain by MS Excel. Later, based on these functionalities, several softwares were developed. Let's start the session. So to know first about well testing or interpretation of well test data, we need to know why this is important in a reservoir engineering perspective. So if you see, there is a tree given here, reservoir engineering, which has two components. One is field services and one is classical reservoir engineering. So in field services, we go for well testing, reservoir monitoring, production forecasting, and field development operations or planning, you can say. So these four components will turn over into classical reservoir engineering methods or techniques where we do material balance analysis for reservoir monitoring, decline curve analysis for pressure for production forecasting, PTA from well test data, and RTA for well test data. So these two are the main topics of discussion in this webinar, especially PTA, of course. So PTA is called as pressure transient analysis. So whatever well test data we get, which is of course the pressure versus time data, we convert that to a pressure transient. So we mimic the wellbore data to reservoir data. The primary functions of reservoir engineering is the estimation of hydrocarbons in place, the calculation of recovery factor, and the attachment of time scale to recovery. So there is something called as recovery factor that is given here. It is being highlighted. So the well test data interpretation will give us the exact number of recovery factor because the primary output of well test data is local permeability. So near the well, what is the permeability, and in the virgin reservoir, what is the permeability? So we will try to modify the static model, which will give us the in place and recovery factor that will change with time depending on several uncertainties. So the well test data is a very prognostic tool which reduces the factor of uncertainty in understanding the recovery factor. The job of reservoir engineer is to produce oil and gas reservoirs in such a way that the recovery is maximized. Of course, PTA will give us a good confidence to maximize the recovery. The key objective of reservoir engineering is to turn the time mirror around, ensuring a coherent image of the future production prediction of an oil field or a gas field or a hydrocarbon field. So, of course, PTA is an integral component of predicting the future behavior of the reservoir. So, we will look at well testing and PTA. So, the objectives of PTA will be to evaluate reservoir pressure, which is either initial or average pressure at the current time scenario, evaluate the reservoir fluid. So, we sometimes take fluid samples. So, they come under MDT and RFT. These are specialized tools which SLB and Halliburton manufactured, and now currently they're being used in the industry, especially for exploratory and delineation wells. So MDT is modular dynamic tester, where we take pressure as well as uh, fluid samples. And even RFT is the same job, but it is from Halliburton. Also, we can estimate reservoir properties like permeability and skin factor. We can also find the reservoir volumetrics from these estimates. So on the right, you can see a pressure recorder, which is sent like a gauge with a slick line. So slick line is a thin line, which diameter is approx 0.138 centimeter. So the diameter of slick line is 0.138 centimeter, slick line. So slick line hangs the pressure recorder, which is a pressure gauge, which is, to be precise in technical terms, it is a memory gauge, EMG, electronic memory gauge. So this EMG records the pressure in the reservoir, even though even the well is flowing or the well is shut in. So when the well is flowing, the pressure declines with time, and when the well is shut in, the pressure increases with time. So we categorize them into different well tests. So we'll talk about that in the future slides. Input data required for PTA would be the bottom hole pressure data that this gauge or pressure recorder gets out of the wellbore. And we also need surface flow rate data. We need fluid properties for the hydrocarbon being produced based on formation volume factor, viscosity, and compressibility of that hydrocarbon. And also we need reservoir properties like thickness, net pay, radius of the boundary, which is also from PTA, then RW, wellbore radius, and fluid compressibility. So the outputs or results from PTA would be the capacity of the well, which will tell us how productive it is. So we can understand whether there is damage or stimulation. We can find the capacity of reservoir based on transmissibility. As I've told you, this PTA output is a main input of reservoir simulation, the static model, which converts to dynamic model when we have time factor. So this transmissibility is actually KH by mu. So in KH by mu, the main component is K. So this K will be now altered. Suppose, say, if it is oil reservoir or oil flow that is happening from the bottom of the surface from reservoir. So this K will be K into KRO H by mu. So this K is the absolute permeability of the reservoir with a single phase, and this KRO is the relative permeability of oil. So the main output of PTA will be this KKRO, that is KO, the oil permeability, effective permeability of oil. That is clearly understood from this PTA based on fine tuning of the data. And we can also find the current average reservoir pressure. We can find the reservoir limits. We can also understand well interference effects based on interference testing. And we can find the well or reservoir specific parameters like wellbore storage, thickness of fracture or length of fault, composite radius and KV to KH ratio. So why well test? Of course, the topic is still unanswered. So well test provides information that can be used for reliable planning of oil and gas production and development and reducing the financial risk in investment. So suppose, say, based on the initial development was drilled, the in place is a figure X. So this in place of figure X is based on the native permeability of the discovery wells. So we have Ki, for example. Now, based on the well test done after 6 months of production, maybe 1 year of production, suppose say this Ki is reduced to a new value Kf. So this drop in Ki to Kf will of course drop our reserve estimates, the in-place volumes. So this in-place volume drop will give us a better, degree of confidence by reducing the chance of uncertainty. So this will reduce the financial risk. That is the main point of, doing well test, which is a cheaper option as compared to drilling a new well. We can also understand, will a new well be productive or beneficial or not based on the current investments that we're going to make for a new well drilling. So important information that well test can provide is the information that is not available in the static model. As I've told you, it increases reliability of geological interpretation and reserve estimates, provides actual and potential productivity of the well tested, collects representative fluid samples of the reservoir for PVT and phase behavior analysis, and of course flow assurance studies, where we can also understand where the wax deposition happens in the pipeline or on the tubing, where is condensate banking happening if it is a gas condensate reservoir. We can also help in identifying well problems such as sand production, asphaltene or paraffin presence, water or gas coning, etc. So these all are relatively possible and easier to find from well test, especially from interpretation. So well test is done during these three phases of the reservoir life cycle. In exploration, we find the reservoir and fluid properties based on samples collected and also reservoir deliverability from reservoir to bottom hole. In appraisal or early stage of field development, we can refine the previous interpretation, and during production, we can opt well test for reservoir management, need for well treatment or interference testing or reserve classification or reserve reclassification. So how is well test done? So the same thing I have talked before. This is the slickline unit that comes from a service company for the operating company. So slickline unit has a thin line. You can see a thin line that is going on the bottom. I'm tracking it with a red line. So this is a slick line, a very thin line. It is very thin as compared to the wire line that we use for logging operations or well intervention operations. So of course, slick line job is also a well intervention job because we are going against the pressure of the well. So a stuffing box at the top will be a secondary well control mechanism. So there is a slick line BOP. Here you can see a BOP. That is slick line BOP because whenever we produce, we generally want we anticipate the production is going up to the BOP. So BOP will be the primary barrier for fluid to flow till the top. If it is unable to stop that flow, the stuffing box will be able to stop that flow further during the drawdown test. So when the well is flowing, this is very critical, BOP and stuffing box. And there's a crossover to join the slickline unit and the wellhead or the Christmas tree. So there's a hay pulley which will give us a tension measurement of the slickline. So as the slickline goes deeper, the tension increases because with depth, the load on the slickline increases. So there's a weight indicator, and this is the pressure gauge. You can see on the right, a person is holding this. So it has two sensors, one here and one here. So these two pressure recorders will record the pressure continuously with time. So there's a least count for this. It is generally 0.2 seconds. So once in 0.2 seconds, the pressure gauge reads the pressure. So the bottom hole survey for measuring bottom hole temperature and pressure of the wells, like FBHP when the well is flowing, SBHP when the well is shut in, static bottom hole pressure, and also build-up test for a long shut-in. So we have the MPG of Lutert type. So Lutert memory pressure gauge is used. MPG is lowered inside the well using a slick line. Initially, dummy run was carried out to check for any obstructions till the measured depth, till the depth we want. This is generally top of perforation. So MD will be the top of perforation. Top of perforation. So we run first a dummy run because we don't want the gauge to, read wrong values, because the dummy run will tell us if there is any obstruction in the tubing. Once it is done, we will run the main gauge. So these are the components of the slick line. So types of well tests. So we're talking about well tests, but we should classify the well tests now. So transient tests include drawdown, build-up, multi-rate tests, interference test, pulse test, DST, and RFT. So among these seven, DST and RFT are done especially in exploratory and appraisal wells. Exploratory and appraisal or delineation wells. But these five will be done in development wells, on a 6 months interval. And stabilized tests include reservoir limits test, which is of course called as EWT or extended well test. So when the well is under observation for more than 4 months or up to 6 months, so we actually are understanding the reservoir limits. They give the actual reservoir boundaries. So we do drawdown test for six months, 1 year interval if the company is so rich. So this EWT will give us the reservoir limits, the actual reservoir boundary. And we also do AOF test to understand the reservoir deliverability, the max deliverability of the reservoir. So whenever you plot IPR curve, so IPR curve is a plot of bottom hole flowing pressure and flow rate. So this AOF test will give us the actual AOF of the well. So AOF is the point of Q where your PWF is 0. So AOF test is done generally in gas wells. And also we can do IPR establishment test. So we will take, the tested rates at different drawdowns. So that rate should match the Vogel IPR that we predict or Fedkovich IPR that we predict. So PTA is used to define reservoir characteristics like perm, damage or stimulation, turbulence in the tubing, inertial and viscous effects, boundaries or reservoir shape, future rate or pressure decline trend. And stabilized sets will give us flow at various pressures and reserves. They give a better estimate of reserves. So single and multi-well tests. So in single test, a sensor is lowered and a single well flows. So whenever we have constant production rate, the pressure drops and it's a stabilized value. That is single well test where it is drawdown test when the well is flowing. But when the well is shut in, you have Q is 0, but P increases initially drastically, but it later flattens down to a stabilized value when the well is closed. Next, single and multi-well tests. So these are called as interference tests. So one well is shut in and one well is flowing. So in the shut in well, there is no production being taken. So in the flowing well, what happens is, so up to this point, the second well is flowing. So pressure drops in the observation well. But after this point, the second well is closed. So the well is shut in instantaneously, and then the pressure starts building up initially, but it will again reach a stabilized value instantly. So when it reaches instantly, that means the boundary of this reservoir is very near to the well that we are testing or that we are observing. So we can also understand what is the actual boundary of the reservoir when they're in interference with each other, when they're connected with each other. So they will give us the pressure communication or communication of these both wells in the same reservoir. And also when two wells are flowing, you can see a drop in bottom hole flowing pressure. So there is a double drop 1 and drop 2. So that confirms that wells are communicating with each other. And especially for drawdown test, we will plot the bottom hole flowing pressure with time, with log time to be very precise. So this will give us regions. I'll talk to you with about these regions in the Excel work or Excel exercise we will do in the later part of this webinar. So we will have we'll have two regions. One is ETR region or early time region, and second is mid time region or middle time region. So early time region, the wellbore effects start dominating or the pressure wave hasn't yet reached the virgin reservoir. But once the slope is now constant in the mid time region, that is the useful data for us, both in drawdown as well as build-up tests. So in build-up tests, so in drawdown tests, you can see the PWF is decreasing with time, log time. But in build-up test, the PWS, so now it is not flowing, it is shut in. So PWS means shut in, flowing pressure. So this will increase with time. So initially the increase will be steeper or faster, and then it will be stabilized. Then injection tests. Injection test when we try to inject into the reservoir to see what is the reservoir capacity or the reservoir ability to take fluid at an injection rate. So injection test also is done to see, suppose we are planning for a water injection, during secondary recovery. We want to see what are the safe injection rates for this well. So injection test is also done to understand the communication with the offset well if it is a multi-test. Then injection fall-off test. So we inject first and then we suddenly stop injection. The pressure falls down drastically in the initial time and then it will fall slowly after it will reach a certain time. So that is injection fall-off test. And then interference test. Of course, it is already discussed. So we have one well is flowing and one well is shut in. But in this case, the shut in well is recording the pressure, not the flowing well. And pulse test. Pulse test is similar to injection similar to interference test, but we have only one active well in this pulse test, and we produce or we open or shut in the observation well or flowing well that is close to the tested well in cycles. So at active well, we first produce and then we shut in, and then we produce and then we shut in, produce. So whenever it is shut in, sorry, whenever it is producing, the pressure drops at the observation well. But whenever it is shut in, the pressure drops at the observation well. Sorry, it will increase. So active well, the flow rate is zero now. The well is shut in, so pressure builds up. Again, it drops whenever the active well is producing. Again, it builds up. Again, it drops. So you want to see how fast is the communication between these two wells. So single rate tests have generally these plots. So whenever we have production, the pressure drops. Whenever we are injecting, the pressure increases. Whenever we are shutting, the pressure increases in single rate tests. But in multi-rate tests, so whenever you produce at a higher rates, so rate 1, rate 2, rate 3. So can anyone tell me how can I increase my well rate at surface? Anyone? So what is the mechanism by
Through
which I can
choke
increase my
size.
well? Correct. Yes.
Through
So
choke size.
we tried to do multi-choke tests. Perfect. So we do multi-choke test, or it is called multi-beam test. So this is low beam, mid beam, and high beam. At high beam, the pressure drop is drastic as compared to the initial reservoir pressure. So that is how we see which choke is, optimal for getting production from this well. That is very important. So multi-rate tests help us in that. So we can understand which rate will give us good optimal flow production rate, the maximum production rate. So whenever you look at IPR equation, so Q is equal to J, the productivity index, into P reservoir minus P bottom hole flowing pressure. So if you just try to get your J, so J would be Q by P reservoir minus P bottom hole flowing pressure. So for J to be maximum, your Q should be higher, and the denominator, which is the drawdown, should be lower. So we do multi-choke study or multi-beam study where we have choke size here 1, 2, 3. Assume choke size is increasing towards the bottom. So we have Q here and we have PWF here. So as choke size increases, your Q will increase. Obviously, let us take 50, 100, and 200 maybe. And let's take PWF. As Q increases, PWF will decrease because we are giving more drawdown. Let's take PWF as 1000 first. Let's take 500. Let's take 100. And let's assume that PR is 2000 psi. So my J would be, in the first case, 50 by 1000, which is 0.05. Second case, 100 by 1500, which will be 1 by 3 or 0.33. Sorry, 100 by 1500, which will be 1 by 15. So, 100 by 15.15, if I'm not wrong. Yes, 1 by 15. 15 nines are. So anyone can tell me what is the value of 1 by 15? Just general value. 100 by 1500. So it will be very less. 0.06. 106. Okay. And the next one, 200.
0.06.
Okay. 0.06. And the next one, 200 by 2000 minus 100, or 200 by 1900 for the third case. 2 by 19.
0.105.
105. So just tell me which case is beneficial for us. Which is giving us more J? That is important. The third one is giving us more J, or the more productivity index. So that will be chosen as the best choke size for this well, because it is giving me a higher rate at a good drawdown, or a acceptable drawdown. That is important. But of course, we need to look at economics, and we need to see how much for how much time it will sustain. That is also important. So the basis of well test is, of course, the pressure and time. So in transient condition, where the boundary hasn't yet reached, pressure will be a function of radius up to which the pressure wave has reached and time. So whenever we draw down fluids, for example, the well is producing, and if I plot pressure versus radius, it will be an exponential declining curve like this. So you want to see up to what radius the pressure wave has reached. So until and unless it has reached the boundary, it will be transient condition. Once it has reached the boundary, we will start seeing the effect of boundary. So where you're at the boundary, your dou P by dou R, the rate of change of pressure with radius is zero. At R is equal to RE boundary, but the change of pressure with time, the rate of change of pressure with time will be constant for all radiuses above this radius, for all R above RE. But in steady state condition, the boundary is really felt, and P will be PE at a constant RE. So your dou P upon dou T will be zero for all R and T above the boundary, R greater than RE. So when R is greater than RE, even though your dou by dou T is zero, you can understand that that is the actual boundary of the reservoir. So we need to stop the EWT. Sometimes some companies also have intelligent gauges where we can get real-time data of the bottom hole gauge. Some companies use gauges and they take the data after the well test is completed. So they can't transmit the data in real time, but some can do that. So in that case, we can be more precise in understanding or estimating up to what time we need to do the well test. If the boundary is already felt, there is no point in putting the gauge in the hole. We can remove that. So in transient flow regime, your pressure drop is exponential with radius. So for transient flow regime, this is the bottom hole flowing pressure equation, which will be Pi, the initial pressure, minus 162.6 Q mu by kh log kt by 5 mu ct rw square minus 3.23 plus 0.87 s. So in this equation, you need to only look at K, and S. So these two are the most important parameters. So don't worry, in the actual course, we will be deriving all these equations. So that is also part of the course. But this webinar is short, so we can't derive everything now. The main focus of us is to understand the fundamentals, and then we'll move on to exercises. So the three governing equations for transient flow regime are continuity equation, transport equation, compressibility equation. So these three will be the basis for deriving equations, where we'll understand what is the distribution of pressure in the reservoir based on the pressure that we get at the bottom hole. So for pseudo steady state, you can see after a time t above radius r, the pressure is now constant. So dou P by dou R is now zero here. There is no change of pressure with radius. That is what this means. But dou P by dou T is constant. So this type of flow regime occurs in a closed reservoir when the pressure transient has moved to all the physical boundaries of the reservoir. Next is steady state flow. So this describes the flow condition where the fluid properties at any location in the reservoir do not change with time. So the properties will again affect the pressure. So in this case, dou P by dou T will be zero. There is no rate of change of pressure with time, but dou P by dou R is constant because fluid properties are now constant. They do not change with time. So if you plot pressure versus time, these are the actual curvatures for three flow regimes. For steady state, it will be constant at R is equal to RE, of course. That is to be mentioned. So for semi-steady state, it will be declining constant at a constant rate with time, but unsteady state will be declining continuously with time. So this P will be Pi. So we have two more things. One is investigation radius. So investigation radius will give us the radius up to which the pressure wave has actually reached. So in time t, we can calculate Ri if the reservoir is homogeneous. So K will be homogeneous in the reservoir. Phi is a constant value. Viscosity of the fluid is a constant value because if we take a single phase fluid, it is constant, and Ct is constant. So we can estimate Ri based on these parameters and time of the test that is being done. So from this, time can be again re-estimated as 948 5 mu ct RA square by K. So at time t is equal to T1, the pressure wave reaches up to this radius. At time t is equal to T2, that is more than T1, it will reach more radius. It will go more into the reservoir. At time t is equal to T3, it will go even more into the reservoir. That is how this is important in PTA, the investigation radius. Apart from this, there is one more principle, that is superposition principle, where we try to understand what is the superposed pressure drop. from the initial pressure. So if you are producing well at different bean sizes, so if you observe the left hand side plot, total delta P will be delta P1 plus delta P2 plus delta P3. But the incremental rate would be Q2 minus Q1 at a new bean and Q3 minus Q2 at a new bean. But of course, Qt will be Q1 plus Q2 plus Q3. So it has a very important principle in actually understanding what is the real flow rate of the well, the total flow rate. So the best example of superposition principle is if you look at these both curves. So in one curve, the well is currently flowing, so pressure is declining, and in one curve, the well is shut in instantly, the pressure is inclining or increasing. So when you add both of them, it will be a superposed pressure. So declining first and then inclining next. Now Pi minus P would be m log T delta T, that is the shut-in time after the pressure after the well is shut in, and before that it will be T plus delta T from the initial condition. So the the actual Pi minus the current P would be m log T plus delta T minus m log delta T. That is the best example of superposition principle. There is one exercise for you. I think you can read the question. Oil flow rate and flowing bottom pressure recorded with time during a multi-rate well test are shown. Let K be the reservoir permeability, H be the formation thickness, and mu be the viscosity of the oil. Delta PT, delta P dt is a constant rate dimensionless pressure drop as a function of time. Total pressure drop till time t, where t is greater than t1, would be which option among A, B, C, D? So as we have seen in superposition principle, at Q is equal to Q1, the well is flowing at a constant beam, but at Q2, the well has changed its flow characteristics. So Q2 minus Q1 would be the new flow rate of the well. Just tell me what will be the option for total pressure drop in this well until time t is equal to t. So up to t1, it is at q1 rate, but from time t1 to t, it is at q2 rate. But until time t, it is at q2 rate. It is at q2 minus q1 rate. That is the most important thing. So up to t1, it will be q1, but from from 0 to t, it will be q2 minus q1. Just understand or observe how we can solve this. Which would be the right answer? So Q total would be Q1 plus Q2, that is known to us, and delta PT would be delta P1 plus delta P2. So for delta P1, Q1 is your rate. For delta P2, your rate is Q2 minus Q1. So we get an incremental rate. So the answer for this will be option A. So for time t, up till time t, it is Q1. And for time t minus T1, for this region, it will be Q2 minus Q1. So up to time t, we are taking it as Q1. And for time t minus T1, we are taking it as Q2 minus Q1. It is the best example of superposition principle that is used practically. Now comes the basics of RTA. So as I've told you, RTA, we will touch RTA in this webinar, but in the real course, we will go deep into RTA. So RTA is a modern tool to better understand the capacity of reservoir. The combination of measured pressure and rate in addition to the relevant analysis structure can lead to estimation of reserves in place. The main and most important for the advantage of RTA is to estimate the reserves in place directly. So RTA is where your rate is a transient, not pressure anymore. So from PI and flow equation of two flowing material balance model, the total reservoir structure can be observed and the reservoir behavior can be recognized. So RTA is science of analyzing production data. In addition to observation of original oil and gas in place, the tool can be used to predict the future behavior of pressure and rate production. Modeling pressure and rates can be used to forecast the reservoir performance and its applicability. So RTA developments were the recent investments in unconventional resources. So we generally use RTA in mostly unconventional resources where the data is very vague, and because the reservoirs are unconventional, they're tight sometimes, they produce water sometimes in case of CBM. So we can replace PT with RTA because we get long transient responses. So in that case, we can't rely on pressure. We should rely on rates of the well. That is how DCA for unconventional reservoirs is done using RTA, rate transient analysis. So the entire workflow is to gather the well test data, which will analyze and quality control the data, deconvolve the data, where we try to fix some values at the spots where we don't have data. We indicate flow regimes. We select the reservoir model. We estimate model parameters. We simulate or history match the pressure response, and we will validate the results. So in this, you can see early time will give us wellbore storage, skin, fractures, partial penetration in case of incomplete perforation. And if it is horizontal well, early time region will give us good response from the reservoir. And middle time region will give us homogeneous properties of the reservoir like permeability. And late time will give us boundary, the leaky boundary, the pressure of the reservoir, and then the rate that the reservoir can max give us. So from this, we will shift now to analysis. So the pressure build-up testing methods for finite or bounded reservoir. The Horner and MBH methods are used to analyze build-up data only for finite acting reservoirs, only for infinite acting reservoirs. This is not true. So whenever we know that boundary is filled, it is not finite anymore. It is not infinite anymore. It is finite. So as I've told you, we plot the bottom hole flowing pressure, sorry, bottom hole shut-in pressure (PWS) versus a new log TP plus delta T by delta T. Can anyone tell me what this is? It has a name, a very interesting and famous
Honor
name.
time. Honor
Correct.
time.
Horner time. Horner time. So Horner has invented this technique where he integrated the log TP plus delta T by delta T, where TP is the production time and delta T is the shut-in time. So this ratio will be now dimensionless. So this ratio will give us a slope in the middle time region, and this slope will help us to understand the reservoir parameters. So we get K directly on the slope, and we can find skin factor by finding the K. And if you can see, the actual pressure increase is not directly higher. It is not linear based on this uh, tangent line to this curvature. It is actually resting at a lower value, but the Horner time is overrating the reservoir pressure. This is called as P star method. So where we find the reservoir pressure, which is a false pressure actually. So Horner's method can be used to estimate the reservoir parameters in finite reservoirs, just as in infinite acting reservoirs. Difference only occurs in late time test data when boundary effects influence the data. For an infinite acting reservoir, an estimate of PT is obtained by extrapolating the straight line section of Horner plot. So whenever we talk about infinite reservoirs, we see that the reservoir extent is so high. So in that cases, this P star method works, but in finite reservoirs, this P star method won't work. For finite and developed reservoirs, the extrapolated pressure is not a good estimate of PT. It will give a high estimate and generally has been called as a false pressure P star. Second is MBH method. So MBH method is the thing where we try to approximate this TP plus delta to delta T. If you can see, the Horner plot may be simplified now if delta T is far less than TP. Suppose say in a well, we are producing for 10 days and then we are shutting the well only for 1 day. So in this case, 10 days times 24, 240 hours is far more than 24 hours. It is 10 times more. So in those cases, we can approximate TP plus delta T to TP. So we will now approximate log TP plus delta T to log TP minus log delta T. So this plot will be now PWS is equal to P1 hour plus M log delta T, whereas in the Horner plot, it is PWS is equal to P star minus M log TP plus delta T by delta T. So this is the difference between Horner and MBH. So MBH is a more realistic way to give us the actual history or the actual prediction of the reservoir parameters when the producing time is not known or can be estimated only roughly. So MBH requires a plot of build-up pressure versus the logarithm of build-up time. So P star will now be P1 hour plus M log TP or M log delta T. So whenever TP is known, delta T is 1. So this is M log TP because log 1 is 0. Now comes the actual game changer of PTA. It is a pressure derivative curve. So whenever we look at pressure drop or increase, in drawdown pressure drops, in build-up pressure increases. So whatever it is, we will find delta P. Delta P is the change of pressure. As you can see, it is given in the blue color, pressure change. So we also find the derivative of this pressure change, which is dou by dou of ln T delta P, which will of course give us T ln, sorry, T dou delta P by dou T. So change of pressure drop to change of time times the current time will be the derivative. So if you plot derivative on log scale and time on log scale, elapsed time from starting, this is called as log-log plot. So both the x are in log scales. So in log-log plot, your blue line will give us the pressure change, which is increasing in build-up data or decreasing in drawdown data. And the derivative curve will first increase in parallel with the pressure change curve. But once the slope will start changing in the pressure change curve, it starts declining until which the slope will now again change slowly. So this will also get slows down. It will be stabilizing, and again slope change a bit faster. It will again go high. So this drop in the derivative curve will give us the start of transient state, or sorry, the start of transition state, where the early time region is ending and the middle time region is starting. So up to 1.5 log cycles, this well-bore storage effect in the well-bore happens. This is the early time region up to 1.5 log cycles. In some test data, you don't get 1.5, you get maybe 1.2 or 1.1. But we need to bring this to 1.5 log cycles because that will be vague in analyzing from the derivative curve. So after you see the data or quality control the data, we will try to understand the extent of this horizontal signature of derivative, because this will give us the radial flow regime at zero slope. The slope of the derivative is zero. That gives us radial flow. And once the derivative again has a positive slope, depending on the slope value, if it is half, it is a linear flow. If it is 1/4, it is a bilinear flow. If it is again 1, it is a radial flow. If it is 0, sorry, if it is 0, it is a radial flow. If it is 1, another flow. So we have different slopes. So the middle time region is mostly important to give us the reservoir characteristics. So we get mostly KH, which is permeability times thickness or net pay, and then we can divide this KH by H to get permeability. That is reservoir permeability. And of course, by getting S, we also get S. By getting K, we get S. So this K and S are very important in understanding the current state of the reservoir. Is it damaged or stimulated, whatever it is. So if you have a slope of negative 0.5, it is unit slope. Sorry, minus 0.5 unit slope. It is spherical flow in the reservoir extent. If it is zero slope, it is radial flow. If it is 0.25, it is bilinear flow. If it is 0.5, linear flow. If it is unit slope, it is well-bore storage or depletion, pressure depletion. So unit slope will give us depletion at the late time region. So linear flow regime has half slope, bilinear flow has 1/4 slope, volumetric reservoir has unit slope, radial flow has zero slope, spherical flow has negative half slope. The start and end of the flow time for every flow regime should then be determined using log-log diagnostic plot or the diagnostic plot related to that flow regime. Currently, the log-log plot is the best accessible approach for characterizing the infinite active radial flow. Because if this radial flow continues up to an infinite extent, that is IARF, it means the boundary is still not realized by this well. So the two basic chances is, one chance would be it is a it is not a boundary dominated flow. Second would be the reserves are so high. So these both can be the best examples for IARF slope in the derivative curve. And also the separation will give us a very beautiful understanding. If separation is high, then skin factor is high. And if separation is low, then skin factor is low. So a reservoir engineer can just look at the derivative curve and just tell the management what is the actual thing happening in the reservoir. Even though he's not fine tuning or not interpreting properly, he can just look at the separation. If it is higher than what he thought of before starting the interpretation, it is maximum skin or positive skin. So we can start planning for a stimulation job, maybe a raising job or fracturing job in the near wellbore region. So this is quite critical. So depending on the derivative signatures, we can also understand special reservoirs. So if there is a drop in if there is a drop in the middle time region, and again drop rebounces to a zero slope region. So this is one composite reservoir. This is another composite reservoir. This means this is dual porous reservoir. This is quite common in CBM reservoirs because CBM has dual porosity. One is cleat, face and butt, and one is matrix. And also when you have naturally fractured reservoir, it is dual porosity reservoir because one is existing porosity of the reservoir or the existing matrix permeability. Second is fracture permeability. So we have two distinctive slopes in the composite reservoir, slope 1 and slope 2 in late time region. And one more thing is that in the late time region, if it goes up, if it has a positive slope, it is a no flow boundary. No flow means steady state boundary or pseudo steady state boundary. And if it is going down in late time region, it is a constant pressure boundary. And if it falls down very fast, it is a leaky boundary. So this late time region signatures will give us a better understanding of what's happening. Later we'll find in this model, depending on the management decision, because they sometimes also dump on us that we need to show these results. So we'll try to also fine tune the model with several approximations. Now starts numerical modeling. So numerical modeling is a interesting tool. Currently, Kappa Sapphire, if anyone of you are using or aware of this software. So Kappa has a software called Sapphire in Kappa suite. So Sapphire has the functionality to numerically model the well test data. For example, say we have taken the build-up data for 24 hours only. Now we want to extend this to 48 hours. Like we want to see 24 hours late after 24 hours, what is the increase in pressure or decrease in pressure? Is it is not recorded by a gauge or the pressure sensor, but we want to see. So numerical modeling will do that. So numerical modeling is we have parameters initialized. We have Laplace solution, that is the IARF or EI function, and we have real solution. We superpose the pressures and rates. We have pseudo functions for gases especially. And now in numerical modeling, we can generate automatic grids. We can initialize the numerical model. We can simulate the uh, like the pressures after the test period, and we can store the animation. So I got an example for you. So I'll show that first, and I'll come to well-bore effects in analytical modeling. So numerical models are quite important in well-test analysis. The main goal is to address complex boundary configurations, but this part of work is actually easily done by any simulator. The problem is to also address what is easily done by analytical models, that is early time response and logarithmic sampling of time scale. So first we enter a top structure map for numerical model. This is the input that is taken. Then we generate the contours. Then we make compartments, which area you want to just understand. Then we discretize, and we generate the pressure distribution in the entire reservoir. And then we divide them into grids. So these are Voronoi grids, which are non orthogonal Voronoi grids. So they're specialized or localized towards the well. That is what you can see here. They're localized towards the well, and they're global at the other parts of the well. And then we generate the actual pressure distribution. There is one animation that can be seen. This is a well somewhere in India. So this well is now undergoing a drawdown test. So you can see the beauty of numerical modeling. So whenever I start my animation, you can see how is the pressure dropping. So the scale like gives us pressure drop in this well. So red is the highest pressure drop. So when the test is now being carried out, the pressure drops because it is drawdown test. So you can see the pressure drops instantly. In time t, it is fastened for this meeting, but yeah, it drops significantly. That is the benefit of numerical modeling, where we can actually mimic the what's happening exactly in the reservoir from the structure map, then generating grids and whatever in numerical modeling. So there are some well-bore effects in analytical modeling. That is what I wanted to focus on now. So well-bore effects in analytical modeling can be due to changing the compressibility of the well-bore fluid. So as you're all aware, whenever we produce fluids, generally gas separation happens near surface depths. So because pressure goes below bubble point pressure. So if you're positioning your your pressure gauge at a depth such that gas separation is happening below the pressure gauge. Suppose this is the liquid level in shut-in well, and gas separation is happening above this level of hydrostatic fluid, and then the gauge is in the gas zone actually. So this will actually read the wrong pressure of the gas. It is not reading the liquid pressure or the oil pressure. It is giving us the gas pressure. but we should know that. So that is mostly dependent on redistribution of phases and the change in storage method from a liquid level that changes to wellbore that is filled with liquid. So we can see a hump in the pressure change curve with time. So this hump will show that there's a phase segregation happening in the wellbore. So this phase segregation is not actually happening in the reservoir. It is in the wellbore because of pressure discontinuity from bottom to surface. So this can give us erratic values of the parameter that we are going to estimate from PTA. That is quite important. To reduce the chance of uncertainty, we have a separate tool called PPD, the primary pressure derivative. This PPD was developed to identify wellbore effects within a pressure response, so they can be separated from the reservoir effects. So this examples can be phase redistribution due to liquid influx after the well is shut in, that is wellbore storage, then gauge malfunction, wellbore cleanup operations, and seismic effects or geotidal effects. So by definition, PPD for any type of reservoir will always either to be constant or decreasing. Thus, any non-reservoir or wellbore effect will appear as increasing PPD. So if you can see here, the PPD drops and then it will increase a bit and then drops again. So phase redistribution is happening in this time region. The data is discarded in this time region and we'll approximate the data from deconvolution. That is what the approach I have used personally in my experience. So that can be used on a daily basis. So whenever you plot PPD, if PPD is having a lump or a hump, at a certain time interval, we will try to eliminate the data by QC, quality control, and then we try to approximate this as a straight line to remove that effect from deconvolution. That is where deconvolution is a bit useful. So I think we are good to go with the theory and the fundamentals. And one more thing is that I've shown you the composite reservoirs where you have zone one of different permeability and zone two of another permeability. So you have derivative response like this. One zone has one slope and zone two has another slope. And again, the reservoir boundary is felt. So composite zones are particularly useful to model a transition zone or transition between fluids such as water around an injector, but from a simulator point of view, it is just a matter of different rock properties against to the ascent of the grid cells. So suppose say we are injecting water in a reservoir and we want to model that in pressure transient sense. So this can be useful when we model using numerical modeling. So let's start examples with MS Excel. Let me share the screen again. So I have two examples for today. One is drawdown test and one is build-up test. So let's look at both of them. Okay, so I hope you can see the screen right now. Please confirm if you can't see the screen. Anyone?
We can see the screen.
Yeah, okay. Okay. So this example is from a drawdown test where you can see the pressure is dropping with time. Look at the plot carefully. This is the initial pressure in the reservoir when the gauge is parked, and then we are monitoring the flowing BHP with time. So this is log time. So log time is going up to 3 hours. Let's change it to logarithmic scale, for example. Yeah, this will be log time up to 3 hours. Okay, so that is log time, and so I have just taken a slope for this curve because assuming that it is fully MTR. So I'll put off this and let's look at it more carefully. So if you just try to just understand what's happening in this, so let's insert a straight line and see how it actually looks. So up to where we need to know up to where is my MTR being observed. So this is the region where MTR is actually being observed. If I just approximate the existing trend line with the new trend line. So I'll change it to black color. Yeah, this is the line which is MTR. So that it is close to the existing trend line that is set for this data. So as I've told you that PWF will be PI minus M log T in drawdown test because the PWF is now decreasing with time. So M is a slope. You can see there are calculations given here. The flow rate currently is 550 STP per day, which is constant, and thickness is 20 feet. Porosity is 0.23 fraction. Compressibility, total compressibility of the fluid is 0.00006 psi inverse. Oil viscosity is 0.42 centipoise. Oil FAF BO is 1.45 RB per STB, and wellbore radius is 0.5 feet. So the main target of this slope that is calculated from this is M will now be 162.6 QB mu by KH. That is given here actually. The slope M is 162.6 QB mu by KH. When we rearrange that, we get K as 162.6 QB mu by MH. So Excel is a bit powerful because whatever slope you can see here is now kept in this, sorry, is going right, is kept here as 120.96. Let me just zoom or scroll up. Yeah. So this is actually negative here. Okay. So from this slope, your reservoir permeability is 22.51 millidarcy. And you can see skin factor is now negative. So this is calculated from transient flow equation where S is equal to 1.151 times Pi minus P1 hour by M minus log K by phi mu Ct Rw square plus 3.23. This actually comes from transient flow equation. So S will now be calculated based on this Pi that is given from this curve, which is 5665, which you can see it's just like extrapolation of this MTR region or the tangent line. So P1 hour you can see from here it is approx 5566 from this data given. At 1.1 hours it is 5566. Now we closely, or we can also do it here. We can draw a vertical line and we can see what is the pressure after 1 hour. So let's draw a vertical line here and see. So shapes, okay. At P is equal to 1 hour, sorry, time is equal to 1 hour. What will be the pressure? Shapes, sorry, shapes, straight line. Yeah. So it will be, if I look at this formula, it will be D21 minus D13. So I have taken P after 1 hour, which is 5599. Oh, it has to be less than 5500. So it should be maybe, let me just try to see, major, convert that to 25 maybe, and see what is the actual value. It is going down anyway. It is like 5475. Let's plug that value, 5475. Now skin will be negative minus 5.74. So its negative skin factor indicates that the well is stimulated. So that is how this Excel workbook helps us to understand what is my permeability and skin factor. So in this course, to be honest, we use Excel, we use also MATLAB. So I'm also adding MATLAB to give you comparison between Excel calculation and MATLAB calculation, because these both are the basis for several simulators developed for PTA in the industry. So we will use both Excel as well as MATLAB for finding slopes and finding permeability and also skin factor. Now let me just open the build-up test data also. So this is the build-up test data that is given here. Delta T is given to us 0, 0.1, 0.35, 0.8, 1.4 till 20. So 20 as build-up test data is given to us. From where we know the formation thickness 35 feet. Flow rate before the build-up has started is 480 STV per day. Porosity 0.18, total compressibility 0.000026, which is 2.6 times 10 power minus 5. Viscosity of oil 1.5, oil FEF 2.2, wellbore rate is 0.5, flowing bottom pressure at delta T is equal to 0 is 2832, which is given here also, you can see this. Then NP before shut-in has started, like when the well is shut-in, 20,000 STB, TP 1000 days. So we have calculated the Horner time ratio, which is log TP plus delta T by delta T. So when we plot this data between x-axis is log TP plus delta T by delta T and y-axis is PWS, the shut-in pressure, we draw a trend line for the mill time region, and we get a slope of 218.42. So if you plug that slope here, and also find my P after 1 hour, which is 3019, I will get my permeability of the reservoir, 33.69. And based on the initial reservoir pressure of this, let me also, just show you how did I calculate the initial reservoir pressure. So we need to set intercept. I'm sorry. So we will move it backward with 20. Okay, backward is towards this side. Escape. Undo. So yeah, we should move it forward. 10. No, it's not going forward. Undo. Let's adjust this scale maybe to mimic the given initial PI. Let's see whether it is right or wrong. So I'm making it maybe 4000. Yeah. So if I just go and insert a straight line, let's see what will we get actually. So inserting a straight line, orange, yeah. So let's again try to increase the major to 50 maybe. Yeah. So if you see carefully, it is giving me somewhere around 3700 something. So that is how we estimated it is 3644, close to 3700. So skin factor is now negative, minus 3.6985. So there's a if statement given here. If the skin is positive, we will display that positive skin factor indicates that well may be damaged, and negative skin factor indicates the well may be stimulated. So that is how we have understood that if suppose I change this to 4, for example, so it will be positive spin factor. That well may be damaged, and negative will give us that well may be stimulated. So that is how this is done. So we will do a lot of exercises in the actual course. The main target of this course is to give you practical insights, not just talk about theory or like make you understand the principles behind well testing and PTA. We will deeply dive into the practical insights of this as a industry practice. That is how I wanted to design the course, and the team also wanted us to design the course. So there's one example from a textbook, Amarnath Chaudhary, which is a very famous book for oil well testing. So I have a example in that textbook. I can give this as a practice exercise for you. So you can see analyzing build-up test using Horner, MBH, and MDH method. So In this, we only use MDH method, not MBH method. It is an extended method for Muscat analysis. So you can see we are given with shut-in time delta T, shut-in pressure PWS, and the drawdown for PI 4510, 4518, and 4535 drawdown pressure. That is PI minus PWS. Sorry, the increase in pressure. Yeah, it is the change in pressure. So from Horner plot, we got a slope of 152 psi per cycle. So we will always get the slope in cycles. So for one log cycle, we get the slope in build-up test. That is quite critical. For one full log cycle, we get the slope that is 152 psi per cycle. So from that, we can estimate the reservoir parameters like permeability and skin factor. So I can give you the answers also for this. So permeability from Horner plot will be perm will be 6.94 millidarcy, and skin factor will be 0.28 for this example. It's a positive skin, positive. And if you look at MDH plot, so MDH plot is where we approximate the TP to be far less than delta T, and delta T will now be the basis on x-axis, shut-in time. So for this MDH analysis, we get the permeability K will be a very close value to the Horner plot. Yeah, here it is 6.94 PS 94 millidarcy, but in MDH plot from the same analysis, you can just find from slope P M is equal to 150 PSI per cycle. It is 150 PSI per cycle here. So of course M is in the denominator, so K will be higher in the MDH plot. It will be maybe 6.96 or somewhat close to 7 millidarcy. 7 millidarcy. And skin factor is of course again positive, like Horner plot. Once this is 7, this will be close to 0.3 somewhere, positive skin. So this can be a good exercise for you if you can just try to solve. The data is given to you here, delta T and PWS. So other parameters that you want, I can give you. Apart from this, Q will be 350 STB per day. Viscosity of oil will be 0.8 centipoise. Then oil FPF, combustion volume factor, will be 1.136. Then net pay or net thickness will be 49 feet. 49. So from this you can calculate your permeability very easily, and porosity is 0.23, and CT, total compressibility, is 17 times 10 power minus 6, and RW is 0.29 feet. Sorry, it's inches. I'm sorry. No, it's feet only. Yes. So this is the data that is available for you, and you can just calculate the the permeability and skin factor. There is one more thing. Since skin factor is positive in this analysis, you can also find out the delta P due to skin, pressure drop due to skin. This is a very interesting conclusion from transient flow equation, where we can calculate this as 0.869 ms. So m is the slope of the plot on the plot in PSI per cycle, and s is the skin factor. So if I just try to understand what is my delta P, it will be 0.869 869 times M is 152 psi per cycle into S is 0.28. So due to skin effect in the near elbow region, I'm getting a drop of around 37 psi in the near elbow region up to the damage exists. This is an additional pressure drop in the drawdown. That is quite important. Okay. So I think I'm good to go with the content for today, and let me just take you through the actual course content. Let me just open the slide. So the content which we have planned for this course is day one, we will be talking about introduction to well testing and Excel as a tool for data analysis from well test data. Then day two, we'll go into well test models and reservoir characterization. We'll look at well test models and we'll calculate we'll solve these data from real fields in Excel to calculate reservoir properties. Then we'll go for advanced well test interpretation where we'll look at log-log plot or log-log diagnostic plots and we'll model them in Excel as well. And we will also look at misinterpretations in analytical modeling, and also we'll look at some more insights on numerical modeling, how they are being used currently in the field level. And then day five, we'll look at case studies and real field insights. I'll also share my experiences when I was working as a young reservoir engineer in the industry in my starting age of my career. So yeah, that is what we wanted to focus on in this course. I hope it is helpful for you. Thank you for your time. If you have any doubts, just let me know. I'm all yours.
Participants, if you have any doubts, please ask.
Hello.
Yeah, yes.
Yeah, can you hear me? Okay. Okay. Actually, my question related to DST, system testing. So
Okay.
in the DST, how many cycle it's supposed to have? The build up, the drawdown. How many cycle at least we must have? And when we just open the valve, the testing valve, there is a increase in the pressure, but it's supposed to be decreased. So what is the reason behind it?
Okay. Okay. So in DST, the main thing in DST is that it is done during drilling. So whenever the well actually has mud, circulating, we have a DST chamber, so which actually tries to shut the well and flow the well in cycles. So as you're saying that we have two flowing cycles and two shut-in cycles. So in flowing cycle, your pressure drops, at shut-in it will increase, then will flow, then it will increase. So your question is that when we suddenly start production, the pressure has to drop, but it won't drop. It will increase. The first and foremost answer for that is that you're already giving an O button for the uh, reservoir fluid to enter the chamber of DST to measure the pressure. So what happens is that when you start taking production in the first cycle, for example, or second cycle, so that pressure discontinuity is there for some time. So for some time frame, your pressure will be constant or either inclining, and then it will start declining. So your realization at the DST chamber actually starts after some time because there is another fluid that is affecting this pressure response. When you instantly start producing in one cycle.
It means that there must be only two cycles,
Yeah,
or
there should be
maximum two
four
cycles, or
cycles only.
minimum two cycles.
Yes, maximum
Only
two
two
cycles. Yes.
maximum. So another
Yes.
fluid, do you mean that the mud or any
Yes,
other
of
fluid?
course. The mud only.
Okay.
The mud.
Okay.
But whenever you have RFT, it can be mud or completion fluid because RFT is generally done only across the pay zone, across the hydrocarbon zone in RFT and MDT
Okay.
that I have discussed before.
Okay. And
Yes.
secondly, about this course that you are going to offer, so when it's supposed to start?
It depends. Once we get registrations and once we fix everything, then we will let you know, depending on the dates. And of
Okay.
course, if you're really interested, we can start it, maybe in 15 days from now, depending on the number of
Okay.
registrations we get. Yeah.
Okay. So how can I contact?
Yeah, the team will help you actually in
Okay, that's
registration.
fine. Thank you.
Yeah.
Thank you.
Any other question? Anyone? So I'll also include DST and its interpretation, right? It's a very great question. Let's not miss that. Okay, I think I can stop now. So I hope I was clear and crisp with the content. So I hope you all will register in the course and make it a grand success. I hope to see you all in the course. Yeah.
Thank you very much.
Okay, thank you very much.